and welcome to Factorising Quadratics Part 3 and video 5 of our video series on quadratics. In this case we're going to look at a couple of special cases for you, just so that you recall and you can maybe pull these out and use them to speed up the process of factorising. So first of all, you recall a couple of things from one of our earlier lessons. A plus b squared is equal to a squared plus 2ab plus b squared. That's the first important thing, and this is called the perfect square. So what it means is if you spot a quadratic in the form a squared plus 2ab plus b squared, you can instantly turn it into that perfect square, and I'll show you an example of that in a minute. The other one was a plus b times by a minus b is a difference of 2 squared, and that's equal to a squared minus b squared. This is the more common one. You'll see that and you'll be able to make a really quick factorization of that in that form. So let's have a look at some examples of these two. A, x squared minus 9. So x squared minus 9 can be written down as x squared minus 3 squared. So it fits that difference of 2 squares scenario quite well. And it means because we have an x and a 3, it means that we have x plus 3, x minus 3. And there we go, we factorised. B. This one's a little bit harder, but the same rule. 25x squared minus 64. Now in this case, again, I might just take the opportunity to write down what is this squared. Well, 25 is 5 squared, x squared minus 8 squared. And so my difference of 2 squares give me 5x minus 8, 5x plus 8. And so again, you can see how this rule can be applied quite easily if you identify that it's a square, subtract another square. And so let's have a look at a further example, but of the other special case. X squared plus 8x plus 16. So now if you recognize here that we've got the x squared, so I'll write this down again, x squared, and the 4 squared, and in here we have 2 times x times 4, 4 coming from there and the x coming from here, well, we can use that perfect square. So this is equal to x plus 4 squared. And it's really important here that we recognise that there has to be a 2, which comes from there, and then it's AB, which in this case is 4 and x. And so we get that 8x. They're a little bit harder to spot, these ones, but it's still an important rule that can help you. And the second case is 4x squared minus 10x plus 25. And this time I've just thrown a minus in here to show you the difference. So I've got 4x squared is 2x squared, 25 is 5 squared. So the big question is, so if you notice a square in each end, you might choose to just consider this, is negative 10x equal to 2 times 5 times 2x? And in this case, the answer is no. It looks like a perfect square because of the 10 and the 25 being half of 10 squared, but the 4x squared component has brought an extra factor of 2 in here, so we can't actually factorise that. So be really careful about using your rules, that you're checking and ensuring that you're using those rules appropriately. To further this example though, let's say you did just look at this and go, oh great, perfect square. 2x plus, 2x minus 5 squared. You should always do just a little visual or quick check of what the solution would actually be if you re-expand it. 2x minus 5 times 2x minus 5, well that would be equal to 2x times 2x is 4x squared, and minus 5 times minus 5 is plus 25, but in the middle you'd have negative 5 times 2x is negative 10x, and then another negative 10x. And so this is 4x squared minus 20x plus 25. And you wouldn't even have to show my working to check that your middle term is what you're expecting it to be. And is it? No. So we have an issue. So there we have perfect square and difference of two squares. There's further examples around on my OneNote and also in your textbook. I do want to show you one other situation though, because this perfect square here is really nice. It exemplifies a special case within quadratics. So let's have a look at let's have a look at a quadratic, standard quadratic, x squared plus 6x plus 9. So here we go, a nice simple standard quadratic. It's actually itself a perfect square. And I've done that deliberately. Now, if we're thinking about this quadratic, what happens, because we've seen the special case here, what happens if that 6x is missing? What happens if it's just x squared plus 9? Well, now you can see we're starting to lean towards that difference of two squares. We have a slight issue with the difference of two squares here, because it's not actually a difference, it's a plus. So we can't apply the difference of two squares, and this can't actually be factorised, and introduces a whole new realm called complex numbers that we won't go into today. But the point is here, if you have a missing linear term, then you get a question like this, and you can apply that difference of two squares if it's a subtraction. If it's a plus, you won't get solutions. What happens though, and this is the big one I'll point out, what happens if the constant term is missing? So what happens if we actually have x squared plus 6x and no constant term, because we haven't talked about this yet. Now, I've seen many cases where people will muck around with this and try and use some factorising technique to get it out, with the constant being plus 0. You don't have to worry about that. If the constant's missing, this is really easy. It's just x plus 6. It's that straight factorisation you've seen before. So it's not really that complex quadratic factorisation anymore. You can just bring out the common factor of x. So be aware of that. And that's special case number 1. I do want to bring your attention. You might be asking, well, what happens if the x squared is missing? So what happens if we just had 6x plus 9? Well, we've got the same thing again. We can take 3 out as a common factor and write this down as 2x plus 3 times 3. But this is no longer a quadratic. So that cross is probably a bit misleading. It's the right factorisation, but this term is no longer a quadratic. So the x squared would never be missing. X squared will always be there, but you don't have to have a linear or a constant term. And if you don't have that linear term, difference of two squares will help you. And if you don't have the constant term, then you can just do a straight factorisation. So there we have it, some special cases for factorising quadratics. All the best.